Welcome! In this video, we'll dive into LeetCode problem number 158, read n characters given read4 to call multiple times. This problem is an extension of a classic file reading challenge, requiring us to handle multiple calls efficiently while maintaining accurate results. Let's explore the problem setup and solution approaches. In this problem, you are provided with an API called Read4. This API reads up to 4 characters from a file into a temporary buffer, buff4, and returns the number of characters it actually reads. If there are fewer than 4 characters left in the file, it will only read those remaining characters. Now, your task is to implement a function called read, which uses the Read4 API to read up to n characters from the file into a given buffer, buff. What's important here is that your implementation of read can be called multiple times without the file being reset in between calls. This means that you need to manage any leftover characters from previous calls and ensure they are used correctly in subsequent ones. Here's how the input and output for the problem are defined. For the input, you are given a file that contains a stream of characters, an integer n specifying the number of characters you need to read, and a buffer buff where the characters will be stored. For the output, your function should return an integer representing the number of characters actually read into buff. This might be less than n if there are fewer characters left in the file. Now let's take a look at some examples to clarify how this works in practice. Suppose the file contains the string ABC and you are asked to read 4 characters. In this example, the output would indicate that 3 characters are read into the buffer, which are a, B, and C. This is because the file only contains 3 characters, so the Read4 API reads all of them in the first call. Your read function then returns 3 since that's the total number of characters available in the file. Now, consider another case where the file contains the string ABCDE and you are asked to read 5 characters. For this case, the function would read all 5 characters into the buffer, returning the array A, B, C, D, E, and the integer 5. Here's how it works: the Read4 API is called twice. In the first call, it reads the first 4 characters, ABCD. In the second call, it reads the remaining character, E. Your function then combines these characters into the buffer and returns 5, the total number of characters read. Finally, let's look at an example where the file contains more characters than the requested number. In this example, the file contains the string ABCDEF, but you only need to read 3 characters. The Read4 API reads the first 4 characters, ABCD, in its first call. However, since you only need 3 characters, your function writes only A, B, and C into the buffer and returns 3. This ensures that any leftover characters, such as D in this case, are saved for future calls. Keep in mind the constraints for this problem: the file and n can be quite large, and you must handle edge cases like an empty file or situations where n exceeds the number of characters in the file. Additionally, since the file is considered a shared global resource, maintaining its state across multiple calls is crucial for a correct implementation. To solve this problem, we first consider a brute force approach. The idea here is straightforward: we continuously call the read4 function in a loop until we've read the required number of characters, n. Each call to read4 fetches up to 4 characters from the file, which we then append to our output buffer. To implement this, we use a temporary buffer named buff4 to store the characters returned by read4. We also keep track of how many characters we've read so far, appending them to the output buffer until we've either reached n characters or hit the end of the file. However, a critical limitation of this approach is that it fails when the read function is called multiple times. The issue arises because any unused characters from the last call to read4 are discarded, leading to inefficiencies and incorrect results. While this approach has a time complexity of O(n), which is acceptable, its inability to handle leftover characters makes it unsuitable for solving this problem effectively. A more optimized approach addresses the key issue from the brute force method, preserving unused characters for future calls. The intuition is to maintain a buffer that carries over any extra characters fetched by read4 but not immediately used. To implement this, we introduce a class-level buffer of size 4, along with a pointer to track the current position within the buffer and a count to indicate how many valid characters it holds. When read is called, we first check the leftover buffer and consume any available characters. If additional characters are needed, we call read4 to fetch more and add them to the output buffer. Any excess characters from Read4 are stored back in the carryover buffer for subsequent calls. The key breakthrough here is realizing that managing leftover characters efficiently allows us to handle multiple calls to read without losing data. This approach still has a time complexity of O(n), but it avoids redundant reads and ensures correctness, albeit with slightly increased implementation complexity. Given the trade-offs, the optimized approach with buffer carryover is the clear choice. The brute force method is too basic and fails to meet the requirements for handling multiple calls efficiently, while the optimized approach is specifically designed for such scenarios. By preserving and reusing leftover characters, this method overcomes the limitations of the brute force approach. An important observation here is that the Read4 API always fetches up to 4 characters, but we don't always need all 4 in a single call to read. Efficiently managing these leftover characters is critical to solving the problem correctly. While this approach does introduce slightly more complexity in managing the buffer state, the trade-offs are minimal. The memory usage is constant, as the buffer is fixed in size, and the time complexity remains O(n), making this solution both efficient and practical. In summary, the optimized approach with buffer carryover provides the perfect balance between efficiency and correctness. It solves the problem of handling multiple calls to the read function by retaining unused characters for future use, ensuring no data is lost and avoiding redundant reads. Its minimal memory usage and consistent time complexity make it an elegant and effective solution to this problem. To tackle this problem, we need to implement a function read that reads up to n characters from a file, leveraging the helper function Read4. The helper function Read4 reads up to 4 characters from the file and stores them in a temporary buffer. If there are fewer than 4 characters left in the file, it will simply return the remaining characters. Our task is to use this functionality to accurately read exactly n characters into a given buffer, buff. To achieve this, we'll start by creating a temporary buffer, buff4, to hold characters read by Read4. We'll also maintain a pointer or index to keep track of how many characters have been written into buff so far, and a counter to ensure we stop reading as soon as we reach n characters. These variables will help us manage the flow of data and handle edge cases efficiently. Additionally, we'll use a pointer to track which characters from buff4 have already been transferred to buff. The core logic involves iterating until we've read exactly n characters. During each iteration, if buff4 is empty, we'll call Read4 to refill it. If Read4 returns 0, that means we've reached the end of the file, so we'll exit the loop. To avoid reading too many characters, we'll calculate chars_to_copy as the smaller of the remaining characters in buff4 and the number of characters still needed to reach n. We'll then copy these characters from buff4 to buff, updating our counters and pointers accordingly. This ensures we always maintain an accurate count of characters read and properly manage any overflow characters in buff4. Handling edge cases, like when n is 0 or the file ends before we reach n, ensures the function is robust and handles all scenarios correctly. This approach is efficient because we avoid unnecessary operations by carefully calculating chars_to_copy at each step, ensuring we only transfer the required number of characters. Another key consideration is proper handling of edge cases, such as when the end of the file is reached or when there are leftover characters in buff4 from a previous call. The data structures we use include the temporary array buff4 to store chunks of up to 4 characters, a pointer to track the position within buff4, and counters to monitor the total number of characters read and the remaining characters in buff4. In terms of complexity, the time complexity is O(n), as we process up to n characters, and the space complexity is O(1), because we only use a fixed-size buffer and a few variables. Let's walk through an example to see how this works in practice. Suppose the file contains the string abcdfghij and we need to read 7 characters. On the first call to Read4, it reads the first 4 characters, abcd, and stores them in buff4. These are then copied into buff, so total_chars_read becomes 4. On the second call to Read4, it reads the next 4 characters, efgh, into buff4. However, since we only need 3 more characters to reach n equals 7, we copy f from buff4 to buff, bringing total_chars_read to 7. At this point, we stop because we've read exactly the requested number of characters. The output buffer, buff, now contains abcdfg, which is the 7 characters we needed. Here's the pseudocode to implement this logic. We start by defining the read function, initializing buff4 as a temporary buffer of size 4, and setting up counters like total_chars_read in chars_in_buff4. In the main loop, we refill buff4 using read4 if it's empty, calculate chars_to_copy based on the remaining needs, and then transfer the appropriate characters from buff4 to buff. After each transfer, we update our counters and pointers accordingly. Once the loop exits, either because we've read in characters or reached the end of the file, we return total_chars_read as the result. This ensures the function behaves correctly and efficiently, handling all edge cases and constraints. This Python solution implements the read function for LeetCode problem number 158, read in characters given read4 to call multiple times. Let's go through the implementation step by step. The class solution is initialized with two attributes. 1. Buffer4, a temporary buffer of size 4 to store characters read by the read4 function. 2. Buffer_size and buffer_index, these track the number of valid characters currently in buffer4 and the index of the next character to be read, respectively. These attributes allow the function to carry over unused characters between multiple calls to read. The read method takes two arguments. 1. Buff, the destination buffer where the characters will be written. 2. N, the maximum number of characters to read. The method initializes total_chars_read to 0, which counts how many characters have been written to buff. It uses a while loop to continue reading characters until n characters have been read or no more characters are available. Within the loop, if all characters in buffer4 have been consumed, self.buffer_index = self.buffer_size, it calls read4 to fetch new characters. The result is stored in buffer4, and buffer_size is updated with the number of characters read. If read4 returns 0, indicating the end of the file, the loop breaks. The next while loop reads characters from buffer4 into buff until either n characters have been written or all characters in buffer4 have been consumed. For each character read, total_chars_read and buffer_index are increment. Finally, the method returns total_chars_read, indicating how many characters were successfully read into buff during this call. This approach ensures that leftover characters are preserved across multiple calls to read and handled efficiently. Here, we start by defining a class called solution, where we handle the logic for reading characters. To manage intermediate data, we declare a buffer array, buffer4, of size 4. This is used to temporarily store characters read by the read4 method. Alongside this, we maintain two integers, bufferSize, which tracks the number of characters currently stored in buffer4, and bufferIndex, which keeps track of the current position we're reading from within buffer4. Next, we define the read method, which takes a character array buff and an integer n as input. The goal of this method is to read up to n characters into buff. We initialize total_chars_read to 0 to keep track of how many characters have been successfully read into buff. Within a while loop, we continuously check whether we have read the desired number of characters, n. If bufferIndex = bufferSize, it indicates that the buffer is empty, and we refill it by calling read4, which updates bufferSize. If read4 returns 0, it means there are no more characters available, and the process halts. Once we have fresh data in buffer4, we begin transferring characters one by one into buff, incrementing total_chars_read and bufferIndex accordingly, until either buff is filled or buffer4 is exhausted. When the outer while loop exits, the method returns total_chars_read, which represents the total number of characters successfully read into buff. This ensures that regardless of how many times the read method is called, it correctly handles the transfer of characters between the internal buffer and the user-provided array. Below this, you'll see a placeholder for the read4 method, which is a mock implementation provided by LeetCode. In practice, this method reads up to 4 characters from the source and returns the count of characters read. Here, it's implemented as a stub, always returning 0, since the actual logic is abstracted away and handled by the LeetCode platform. This design ensures that the focus remains on how to manage multiple calls to read effectively using the internal buffer. To begin, let's walk through an example where we want to read 6 characters from a file containing the string ABCDFG. Initially, we set up the required variables. The buffer4 array, which temporarily holds up to 4 characters, starts empty. Variables buffer_size and buffer_index are both initialized to 0 to track the state of buffer4. We also initialize buff as an empty list to store the final characters we read, and total_chars_read is set to 0 to track the total number of characters collected so far. On the first call to Read4, the function fills buffer4 with the first 4 characters from the file, A, B, C, D, and it returns a buffer_size of 4, indicating that 4 characters were read. After resetting buffer_index to 0, we then copy all 4 characters from buffer4 into buff. At this point, buff contains A, B, C, D, total_chars_read is updated to 4, and buffer_index moves to 4, marking the end of the current buffer content. Next, since we still need 2 more characters to reach our target n equals 6, we make a second call to Read4. This time, Read4 reads the next part of the file, filling buffer4 with E, F, G, and returning a buffer_size of 3, as there are only 3 characters left in the file. After resetting buffer_index to 0, we copy the first 2 characters from buffer4 into buff, as that's all we need to reach our target of 6 characters. Now, buff contains A, B, C, D, E, F, total_chars_read is updated to 6, and buffer_index moves to 2. At this point, since we've read all 6 characters requested, we return total_chars_read as 6, and the final buff contains exactly the characters we wanted, A, B, C, D, E, F. Now let's explore a second example where we make a follow-up call to read 5 characters after already reading 6 characters from the same file. To start, the leftovers from the previous read are still in buffer4, which contains E, F, G, with buffer_size at 3 and buffer_index at 2, indicating that only G remains unused. Once again, we initialize an empty buff and set total_chars_read to 0. The first step is to use the leftover character in buffer4. We copy G into buff, updating buff to G, total_chars_read to 1, and buffer_index to 3, which marks the end of the available characters in buffer4. To continue reading, we call Read4 again, but since the file has no more characters, Read4 fills buffer4 with empty values and returns a buffer_size of 0, indicating that we've reached the end of the file. At this point, because there are no more characters left, we exit the reading loop. The final result of this call is total_chars_read equal to 1, and buff contains just G, which was the only character available to read. Now let's consider a third example where we attempt to read 3 characters from a file that contains fewer than 3 characters. In this case, the file contains only the string ib, so we expect to read as many characters as possible without exceeding the file's length. As usual, we start by initializing buffer4 as empty, setting both buffer_size and buffer_index to 0, and preparing an empty buff and a total_chars_read counter set to 0. This setup is ready for the first call to Read4. On the first call to Read4, the function fills buffer4 with A, B, and returns a buffer_size of 2, as there are only 2 characters available in the file. After resetting buffer_index to 0, we copy both available characters from buffer4 into buff. At this point, buff contains A, B, total_chars_read is updated to 2, and buffer_index moves to 2. Since we've reached the end of the available characters in buffer4, we make another call to Read4. However, because the file is now empty, this call returns a buffer_size of 0. With no more characters left to read, we break out of the loop. The final result for this example is total_chars_read equal to 2, and buff contains A, B, which represents all the characters we could read from the file. The key insights from these examples highlight how this solution handles different scenarios effectively. First, the buffer4 array plays a crucial role in storing leftover characters between calls, ensuring that no character is lost. Second, the combination of buffer_index and buffer_size allows us to manage the state of buffer4 efficiently, enabling seamless reuse of any leftover characters. Finally, this approach is robust enough to handle edge cases, such as files shorter than the requested n or situations with leftover characters from previous reads. These elements together ensure that the solution is both efficient and reliable for multiple calls to the reading function. To analyze the time complexity of the read function in this problem, we start by breaking it into 2 key operations. First, reading from the Read4 function. This function reads up to 4 characters from the input stream each time it is called. However, it doesn't depend on the number of characters requested by the read function, which means each read4 call takes constant time, or O1. The second operation involves copying those characters from the internal buffer, buffer4, into the output buffer, buff. This step is proportional to the number of characters actually read, which is at most n. Additionally, if the loop in the read function needs to fetch more characters, it will repeatedly call read4 until all n characters are processed. Since each read4 call handles up to 4 characters, the number of calls is approximately ceil, n/4. Together, these steps form the basis for the time complexity calculation. Now, combining these observations, the total time complexity depends on both the number of read4 calls and the copying operation. In the best case, if n is small and fits entirely within a single read4 call, such as when n equals 4, the function completes in O1, involving just one read4 call and minimal copying. However, in the worst case, when n is large and multiple calls to read4 are required, the time complexity becomes proportional to n. This happens because the total number of read4 calls is approximately ceil, n/4, each taking constant time, and up to n characters are copied one by one. Therefore, the overall worst-case time complexity simplifies to O(n). Moving on to space complexity, we observe that it is influenced by the internal buffer and temporary variables. The internal buffer, buffer4, is a fixed array of size 4, contributing O(1) to the space complexity. Similarly, temporary variables like total_chars_read, buffer_size, and buffer_index also use constant space. Importantly, the output buffer buff does not count toward the space complexity of the function since it is provided by the caller. With no additional data structures that grow with n, the overall space complexity is O(1). To summarize the time complexity across different cases, in the best case, when n equals 4, only one read4 call and minimal copying occur, resulting in O(1) time. For the average case, the function performs approximately ceil, n/4, read4 calls and up to n copies, leading to O(n) time. Similarly, in the worst case, when n is large, the function performs the maximum number of reads and copies, still resulting in O(n) time complexity. When comparing this approach to a naive solution, we can see how the proposed solution is more efficient. A naive approach might involve directly calling read4 in a loop and copying characters to buff. This leads to inefficiencies, such as making redundant read4 calls and discarding unused characters after each call. Additionally, it fails to reuse leftover characters, introducing unnecessary overhead for processing the input. In contrast, the proposed solution uses an internal buffer, buffer4, to store leftover characters from previous read4 calls. This allows the function to reuse these characters in subsequent reads, reducing the need for redundant read4 calls and ensuring that characters from the input are read only once. This optimization significantly improves efficiency while maintaining the same functionality. To mathematically prove the time and space complexity, consider the number of characters requested, n. The number of read4 calls required is at most ceil, n/4, with each call taking constant time, O(1). Copying characters from the internal buffer to the output buffer takes O(n) time in total. Combining these steps, we arrive at a total time complexity of O(n). For space complexity, the internal buffer and all additional variables are constant sized, contributing O(1) space. Since no data structures scale with n, the total space complexity remains O(1). This efficient handling of both time and space ensures the function performs well even for large values of n. When working with this problem, there are a few common mistakes that can trip you up. First, not handling partial reads from read4 is a frequent issue. Since read4 may return fewer than 4 characters when the end of the file is reached, failing to account for this could lead to reading garbage values or even infinite loops. To avoid this, always check the return value of read4 and stop reading either when you've reached the desired number of characters or when fewer than 4 characters are returned. Another mistake is overwriting the output buffer. If you append characters directly to the destination buffer without managing indices properly, you risk overwriting previous values or causing index mismatches. To fix this, use a separate buffer to temporarily store the characters read by read4 and copy them carefully to the output buffer based on your current write index. Lastly, some solutions read more characters than needed. If you continue calling Read4 even after the desired n characters have been read, it wastes time and processes unnecessary data. To handle this, stop reading as soon as the total number of characters matches n. Additionally, ignoring edge cases can lead to errors or incorrect results. For example, scenarios where n is 0, the file is empty, or the file size is smaller than n might not be handled properly. To address this, include explicit checks for these situations and return early if necessary. Another common oversight is assuming that Read4 is always reliable. If you assume it will never fail or will always return exactly the required number of characters, you might develop an overconfident solution. Instead, always validate the behavior of Read4 by checking its return value. If applicable, consider handling exceptions to account for unexpected behavior. This problem also provides several valuable interview insights. One key theme is pattern recognition. The challenge lies in managing buffers, handling partial reads, and implementing iterative logic while being mindful of edge cases. These are common requirements in file manipulation or I/O related problems. Interviewers often expect you to start with a brute force solution and then optimize it. For example, you can minimize the number of calls to Read4 by carefully managing the buffer. Demonstrating awareness of edge cases, such as files smaller than n, empty files, or when n equals 0, is crucial. Discussing these edge cases during your interview shows a comprehensive understanding of the problem. Equally important is clear communication. Explaining how you manage indices and buffers ensures your thought process is visible and prevents misunderstandings. Related problems to this one include LeetCode 157, which is a simpler version of this problem focusing on a single read, and LeetCode 158, this very problem, which builds on the simpler case by introducing a persistent buffer across multiple calls. Other related problems that test similar skills include LeetCode 28, which involves finding the index of the first occurrence of a substring and focuses on string manipulation and buffer management. Another is LeetCode 10, which deals with regular expression matching. While it's not directly related to file I/O, it tests your ability to handle iterative logic and edge cases in a similar way. Now, let's examine some alternative approaches. One is the buffered approach. Instead of appending each result from Read4 directly to the output buffer, you can use an intermediate buffer to store excess characters that are not immediately needed. This reduces redundant reads and improves efficiency. The trade-off is that it's slightly more complex to implement due to the additional buffer management. Another option is the recursive approach. By using recursion to read characters until the desired n is reached, you might find the logic more intuitive for handling partial reads. However, this approach comes with higher memory usage because of the recursive stack, and there's a potential risk of stack overflow for large inputs. Finally, the two-pointer technique is another helpful approach. Here, you use 2 pointers to manage the read and write indices within the buffer. This gives you precise control over where characters are placed, ensuring that you avoid overwrites and make optimal use of the buffer. While this technique requires slightly more bookkeeping, the trade-off is worth it for the improved accuracy and efficiency it provides when managing the output buffer. Great job! We've successfully tackled problem number 158 by implementing an efficient solution that handles multiple calls to Read4. Remember the importance of state management and buffering when working with I/O operations. Thanks for watching, and don't forget to like and subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!